Welcome to the September 27th Math 265 Zoom. Da, 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 da. All right, so let's, as usual, this is just your chance to, yep, got some tats. This is your chance to ask me questions. You guys can do well on the test. Um, who wants to start us off? You can use audio, or you can just do something in the chat. So related rates, 2.7. All right, let's look at 2.7. So we have related rates and then also 2.7. So let's see what those are. I'll make sure I get to both. So I'm going to go to 2.7 and we had one. All right, so number 4. Let's take a look at that one. Okay, so let's take a look at number 4. I'm going to share the screen. Um, Here you go. This is 2.7, number 4. A particle is moving along the curve y equals 5 square root 2x plus 3. As the particle passes through the point 315, the x coordinate is changing at a rate of 4 units per second. Just copying the information down. Find the rate of change of the distance of the particle from the origin. All right, give me a second here. All right, you got it, Kill. Beautiful. All right, I'm going to unshare, and I'm going to go to my overhead camera. Okay. There's a question regarding which chapters are focused on more. It's hard to say. I think it's all pretty evenly mixed. At the end of the discussion tonight, I'll kind of give you a general overview. So let's work this question here. We've got a function y equals 5 square root 2x plus 3. And we're told that at the x dt, the rate of change is 4 units per second. That's for the change in x. We want to find the rate of change of the distance from the origin. So the distance is actually a function. Well, I'll use the Pythagorean formula for that. Okay, but notice that y is already given up here as 5 times square root 2x plus 3. So we'll pop that into the y position. That way we have a single variable function d of x. And there's actually a couple ways to do this question, I'm thinking now. But anyway, let's clean this up a little bit. It's I'll put the 25 here, it's 50x plus 75 all under the square root. So all I did was just replace y with its equivalent in terms of x. And all right, so what I'm going to do next, I'm actually going to take a derivative here with respect to t. Believe it or not, this is actually an implicit form. And I'll do it with respect to t. dd of dt is equal to, now I have to take the derivative of this whole guy, so it's going to be 1 over 2 square root the whole thing. And then the chain rule, 2x plus 50. And then I have dx dt. That's by the chain rule also. So let me pause there for a moment. So there's a comment here. It's amazing we can add a variable such as t with the power of derivatives. Yeah, you can actually. A lot of times, especially if you move on into Calc 2 and Calc 3, a lot of times functions are defined The variables are actually defined in terms of a separate variable time. It's actually pretty common. And the question also, should we expect a lot of word problems? You should expect a couple. All right, so let's work this thing out. So really at this point, I just need to plug in the numbers. I just got to plug in the two, I'm sorry, the three. We have, let me break down three for X. And I'll just do that. And then the four comes from up here. That's your dx dt. Oops, I forgot to put the three in here. Sorry. And I'm sorry for the mess. Let me clean it up here. It's going to be 1 over 2. That's going to be 9. 150 plus 159 plus 75. That's 225, 234. I'll do this in my head. This will be 9. So, and then, of course, we have the 4. Let me double check that calculation here. So 9 plus 150 plus 75. Yep, looking good. And so then I just going to work this out. It actually comes out to be 36 on top and 2 over red, 234 on the bottom. And give me a second here. And I get 1.1776 units per second. And that sounds about right. So okay. Does this help? I know I kind of ran through that a little bit quick. Does this help understand how related rates work? Feel free to pop in with a question on this one if you have one. Um, maybe I can do another one, just kind of again, just to kind of give you a selection. Um, let's look at another one. So we'll go back to 2.7 again. I haven't forgot the other questions, but let me go back. How about, I don't know, how about number, I'm sorry, I forget what the questions were asked. 2, 7, 4, 7, and 8. All right, let me. I tell you what, number 8 is a lengthy question, and you know what I think I might do is I might prepare a PDF of that because otherwise we'll spend probably 15 minutes on that one alone. So I think I'm going to do a PDF on that one. I'll have it probably sometime this evening. I don't know. Number 7 is a good one. So I'm going to share it. 2.7, number 7. A street light is at the top of a 20-foot pole. I'm going to draw a schematic here. A 6-foot tall woman is walking away from the pole with a speed of 4 feet per second. How fast is the tip of her shadow moving in feet per second when she's 40 feet from the base of the pole? Okay, let's share here. Okay, so this one, trying to find the actual, we're trying to find this figure right here. So the tip of her shadow, this is actually, okay, here's the woman. Here's her shadow. Here's the light pole. And here's the light. Um, so she's walking away at 4 feet per second. Her shadow is getting longer. And again, this is one of those questions. There's a few ways to do it. A lot of it just relies on geometry. We have 6 and 14. I'm sorry, 20. And then I'll call this guy X and this guy Y. And so in this case, dy dt is 4 feet per second. Okay. Um, and so what we want to do is we want to come up with a relationship here. I'm kind of thinking this out myself. Give me a second here. Um, we have, oh, let's do this. All right, so we have proportions y over 6. So we do y over 6 is the same as x plus y over 20. Does that ring a bell from geometry? We're doing, what do they call those? Similar triangles. So these are similar triangles. The corresponding sides are proportional. Now the big triangle has proportion x plus y. And if I want, I could actually just go through and cross multiply, get rid of the fractions. And you know what? It actually collects, actually turns out to be a pretty basic form here. That's going to be 14y, which that's equals 6x. And if I wanted to, I could do y equals 6 over 14x. Okay. You know, I can even reduce that. What's that, 3 over 7? So if I do a derivative now, if I take the derivative with respect to time, the derivative of 3/7 x is just 3/7, but times the x dt. Okay. Um, I know that dy dt from the given problem is 4. So that allows me to solve for the x dt. So if I just multiply by 7 and divide by 3, I get 28 over 30 is dx dt. Sorry for my camera here. So I'll put some circles around it. But notice, and I'll say that's not quite our answer. Our answer is actually the overall change in x plus y. So if I take these two together, so the change in the tip of her shadow is really governed by not only her but also her distance from the light pole. So you just add them. So the overall change in the long side here is going to be dx dt plus dy dt. And that's going to be what do we got here? 28 over 3 plus 4. That's 12 thirds. So that's 40 over 3. It's about 13 and a third feet per second. Okay. Um, Question, how do we know to use dy dt? Well, you know, if I take the derivative of this with respect to time, and again, you know it's time because there's this time element in the problem, seconds. And so that means that both variables are independently functions of time. And so when I take the derivative, I really have no choice. I have to take the derivative with respect to time. And so I can't just do dy dx because dx by itself is not really anything unless I have the time element built in. So I have to treat these both as rates with respect to time. And to be honest with you, there's actually a few ways to solve this question. I may have beaten this with these stick too much, but I know it seems to work. So, okay. Again, I'm kind of running through this fast. Are there any questions? You get 40 over 7. Uh, it may, you know what, it might, I get 13 over 13 and a third. I get 40 over 3. But it may be your question is because the numbers vary. Your numbers might be different from my numbers. You know what? I'm gonna check it too. Let's see. I actually forget how to look up the answer. Um, I don't remember how to do that.
So for this one, it
Yeah.
seems like we're just looking for the speed at the tip of kind of x plus y.
Yeah.
So I calculated it where your y, which isn't the y scale, but it's just a random variable name, would be equal to 3/7 x. And then the length would be x plus 3/7 x, which would then equal to 10/7 x. And then I took the derivative of 10/7 x. And I thought it was dx over dt equals 4, which is how I got
That's
40 over
actually a
7.
good point. You know what? You got me thinking now. I'm trying to think what would be the wrong showing.
Before I was doing the distance formula, but then I learned I didn't need to do that because we weren't
No.
looking at the hypotenuse at all.
That's actually a really good point. You know what? I'm gonna have to ponder on that because it seems like what I did feels right. The answer feels correct, and I don't see a flaw in your thinking, which may mean there's a flaw in my thinking. Um, so I have. Let me get back to you on that one. I apologize. It's one of those times I feel like I'm not sure. I'm not 100% sure. I may have to actually revisit this. Who asked that? I forgot who asked that. Was that Michelle? Yeah. All right. I'll get back to that. I apologize. Now you've got me kind of wondering. So I'm going to put like, I don't know, what's the international symbol for confusion? That. Okay. Um, let's see. We were asked about section 2.6, scrolling up, 2.6, 1, 3, and 4. Let me go to that. Um, we back out of 2.7 here.
I think if it helps at all, like I'm struggling a little bit on these word problems too, and I think the reason
Okay.
why I'm having a hard time with them is um, getting from the point like I can take a derivative just fine of an equation, but setting things up in a way that makes sense and setting it up in the beginning so that it's all ready for you. I think that's the hard part.
That
So
is not surprising. The biggest challenge is to take something that's written in words and translate it into a mathematical expression.
right,
And that, unfortunately, that's not a formulaic process. That's something that you kind of have to pull information from your past knowledge. For example, the question where the first one I did tonight, um, I had the I had to just use the Pythagorean formula. Now, in the problem, it didn't say Pythagorean formula, but suddenly the distance, because we were thinking, this object is moving away from the origin and it has both an X and a Y coordinate, that would be a triangle. And and a question like what we did here just now with the again, here's kind of similar triangles. I find it helpful as best as I can to um, draw a schematic. Oh, you know what, Michelle? Actually, I completely ignored this 40. All right, you know what, people? I'm going to have to punt on this one. And this will be another one that I'll prepare a PDF for because I completely ignored that 40. I actually worked it out generically using X and Y. Ooh, all right. Well, that's my bad. I will send you all a PDF on that one too. So I've got some homework tonight. I will do this one as well. Let me make a note to myself. So this one and the one on the water. I hate when I do that. All right, well, anyway, check your email in a couple hours. I'll have something for you all. Yeah, I completely spaced on that 40. And as in regards to just setting up, again, that's just something that takes a lot of practice and you know, kind of some knowledge of basic geometry. Um, I wish there was a way to just tell you, just, you know, put it into this algorithm and it works, but you can't. It has to be something that, again, you're pulling some information like from previous classes, geometry, for example. All right. Oh, you know what? Let me share the screen here. So this question, I'm going to go back actually to the, I'm sorry, actually, it was 2.6 number 1. Let me pull that one up. We have 5x squared plus 2x plus xy equals 3. We're told that y at 3 is negative 16. We want to find y prime at 3. Okay. I will stop the share. Now this one, there's no implied time element. So we're going to differentiate with respect to x, and we're going to do each one of these kind of its own little differentiation. The derivative with respect to x of 5x squared is just 10x. Now the question is, isn't there a chain rule? Yes, there is. You would follow that with dx, which is 1. So you don't need to do that. For here you have 2x, the derivative is 2. And again, dx, which is 1. Now here you have a product. So I'm going to have to fit it in here. So we first times derivative of the second. Now that is, I can't just write 1 for the derivative of y. It's actually dy dx. Or you could think of it as 1 dy dx for the chain rule. Plus the second, which is y. Now at that point, I'm not actually taking the derivative of y, so I don't need to worry about it. Times the derivative of x, which is 1. Or if you like, dx dx. And then the derivative of 3 is 0. Okay, let's clean this up. We've got 10x plus 2 plus dy dx times x plus y equals 0. Let's get the dy dx isolated. Let's take all of these guys and move them to the right side. So they're all going to get subtracted out. And then let's divide out by the x. And that's our implicit derivative in general form. Now what we do is we plug in, we're told a point is 3 and negative 16. That means x is 3, y is negative 16. So you just pop them into place. And there you go. You get 16, take away 30, take away 2 over 3. That's negative 32 on top. I'm sorry, negative 16 on top. So 16 take away 32 is negative 16 over 3. And that looks like it's our answer. That's our slope. That's our y prime at 3. Okay.
Really quick, how do we get x equals 3 again, please?
That was given in the problem right here.
Okay.
So this was actually a given.
Yeah, okay, cool.
I see it. And oh, you know, I'm going to make a comment. I'm actually going to share the screen here. The question was from 2, 6, 1, 3, and 4. I just did number 1. I'm going to make a comment to number 3. These are all kind of similar questions. And there's a lot of confusion. I think with the trigonometry, you just have to get used to them. And you know, one of the old-fashioned method of writing down each derivative 10 times oftentimes works. The derivative of the sine function is cosine of whatever the argument is. The derivative of cosine is negative sine. A lot of people get those backwards or forget the negative altogether. Otherwise, it's really the same kind of steps. In the first term, where you have 7x plus sine y, I'm sorry, 7x times sine y, you're going to have to use a product rule. So you would say first 7x times derivative of sine y, which would be cosine y times dy dx. And then you proceed, then you do the second part, sine y times the derivative of 7x, which is 7. There's not much, they all vary just slightly. You'll notice very slight changes in the questions here. So you're gonna get slightly different answers, but yeah, keep track of it. And then number 4, same thing. You take the derivative of sine xy 5. The derivative will be cosine xy to the 5. Then you have to follow that with a chain rule. And you actually have to perform the product rule on xy to the 5. And that's, again, that's going to be, you have to separate that out into a couple of terms. And you just have to be really careful with the algebra. So with the trig, just be very careful. I've always told my students, make sure you know everything there is to know about sine and cosine. You can always construct tangent from that by taking their quotient, sine over cosine. Then the other 3, honestly, you use the secant a few times, but the other 2, the cosecant and the cotangent, I almost never use them. And I always just rebuild them from scratch. So if you ever have me, I teach a lot of Calc 3 in this at ASU. If you ever have me for Calc 3, I'll probably emphasize that. I'll say just do everything in sine and cosine. Don't mess around with cosecants and cotangents. They're hard. So, all right. Let me go down. I know there's a lot of messages. I'm sorry, I'm probably not doing a very good job of keeping up with all the messages. Somebody suggests number 2.8, number 2. All right, let's take a look at that one. All right, Edfinity, play nice with me, all right? Every time I go back, it takes me to the main screen. So 2.8, number 2. All right, that's a fun one. All right, let me bring that one up. Let me share the screen.
I had a quick question that
Yeah, sure.
was in the chat. Are we okay to use the canned examples in Desmos?
You should be. Have you had any
Okay.
trouble getting to them?
No, no. I just was curious if that was something that was going to be flagged um, by the proctors.
I see what you're saying.
Because it has the unit circle in there with all of it solved. And I was just curious if you
Yeah.
pulled
Oh
that up
gosh.
from.
You know what? Um, I don't think you'll be flagged, and there's really no way for me to govern that. All I ask is you guys do this honestly, show your work, you submit your work to the to the Canvas site. Yeah, excellent point. I don't know. Yeah, just make sure that you know what you're doing. Honestly, I have no idea how much is in Desmos in terms of all the canned examples. So, all right, let's look at number 2 here. This is from 2.8. And we're going to use linear approximations, that, i.e. the tangent line, to approximate root radical 81.1 given the function y equals f of x, square root x. Okay, so I'm going to stop the share. All right, when you do linearization, don't let the terminology intimidate you. It's just equation of the tangent line. That's all it is. All right, so the idea here is we want to look at 81.1. So pick x to be 81. Why? It's convenient. You know what the square root of 81 is? It's 9. So that means you have a point 81 comma 9 on your graph. Now we need the slope. So we do that by taking the derivative, 1 over 2 rad x pop in the 81. You get 2 times 9, which is 18. All right, yay, you got the point, you've got a slope. Pull that into the slope point formula for a line. All right, just put the numbers in place. You got 1 over 18x, and then 81 over 18 is 9 over 2. Make sure you get that negative. I'm going to add 9 to both sides. And then that should be that should be plus 9 over 2. Now I'm going to I am actually going to go decimals here. I'm going to show you something. All right, so keep that in mind. Give me a moment here. I'm going to have to bring decimals up. I'm going to give me a second. I have to share it now. I'm going to type in f of x equals square root of x. And then in the next line, I'll call the tangent line, oops, geez, what's that? It's 1 over 18x plus 9 over 2. Now I'm going to zoom out here to 81. Give me a moment here. I think we'll find it. All right, there we are. Now, if I zoom way out, you can see the tangent line in blue and the graph in this red. It's not obvious, but they're actually tangent right there at 81.9. But notice how close the tangent line mimics the curve. And so points on the tangent line are extremely close to the actual points on the curve. The idea being is that if I want to estimate 81.1, I use the curve. I'm using G for the tangent line. If I want to know the actual value to the of 81.1, look how close they are. Look at the actual value here is the 9.00555384194 yada yada, whereas the estimation is 9.0055555 forever. They actually are the same out until the 6th decimal place. They're within a millionth of each other. Okay, that's actually really good. In fact, check this out. If I zoom in here, I'm zooming in at 81.9. So well, yeah, right there I had it. Can't seem to land on it. But look how close, even if I go out a few units either way, I still get really good estimations. For example, an estimate of the square root of 63 using the tangent line, it just gives me 8. All right. The actual, oops, I didn't mean that, of 63 would be 7.937. Okay, that's still pretty good. It's off by 0.063. Not too shabby. Okay. Again, the point is that near the point of tangency, the tangent line and the curve itself are almost indistinguishable. That's what linearization is. When you get to Calc 2, you'll see what are called Taylor series, and that actually expands the idea to use other curves as approximation curves. It's really nifty. You'll like it. Okay. All right. Well, that's kind of the idea of that one. Oh gosh. I'm just going through the chat here. Again, I'm trying to do 4 things at once. I'm in the process of memorizing unit circle. Yeah, it does take some memorization. There are patterns, and writing them out over and over again helps. You want to get to a point sooner than later where you just know them. If I say sine of pi over 6, you know it. Cosine of pi over 3, you know it. Let's see.
Question really fast.
Uh-huh.
For that problem that we just did, what would be the similarity or difference? Because I was doing some research on doing this because I was having some hard times doing implicit differentiation and then this. And one of the equations that was provided was the f of a plus f prime of a. multiplied by x minus a to find that same result, would
It's
that,
identical. It's actually
it's
the same.
identical?
It's like same
Okay.
exact thing. And you know what? I'll be honest, that's always bugged me why they treat it as a whole different thing. It's absolutely 100% identical to find the equation of the tangent line.
Okay, perfect. Thank you.
You are 100% safe.
Perfect. Okay, thank you. Because that's what I've been doing this whole time. And like, wow, you made it look so much easier.
Yeah, yeah. No, that's all it is. All right, so we have a question 3, 2, number 2, and 3. Let's take a look at that one. So hopefully they're easy. 3, 2, number 2, and 3. Oh yeah, the famous one. All right. Let me share it. So the function you're given is f of x equals square root x minus 12. You're asked to find a few things, f inverse of 12. You're asked to find the derivative of the inverse at 12. And then you're asked to find some information about the general inverse function, its domain and range and all that goody stuff. You know what? This is another case where I think sometimes the explanation gets confusing. I'm going to show you something kind of cool here. I'm going to draw, that was terrible. All right. I'm going to draw a curve. There you go. We'll call this guy f of x. If I draw the 45-degree line to the origin, then the inverse curve is actually a mirror image of that across the 45-degree line. And there's some nice geometry that comes into play here. If you have a point AB on the F curve, then its corresponding point is BA on the F inverse curve. And if you know the slope here is M, then the slope here is just the reciprocal. That's it. That's all. So if you just can identify the parts, then you'll be in good shape. Now, in this particular example, it's actually feasible to work out the inverse because algebraically it's not that hard to do. But I want to just challenge us. F inverse of 12. Let me ask you this: Can you determine an x value for which, when you plug it in, you take away 12 and you take the square root, you get 12? And you might be able to do this just mentally. What so you would want 144 in here. It's actually not critical. Well, actually, let's go ahead and do it. You want 144. That means x would have to be 156. Okay. Because 156 take away 12 is 144, and then the square root of 144 is 12. All right. That means this is a point on F. That means if I reverse them, is 12 comma 156 is on F inverse. Okay. Now check this out. Actually, I did need to know the x because here's what I'm going to do. I'm going to take the derivative of this function. It's 1 over 2 square root x minus 12. Now the chain rule will just be a 1, so I'm okay there. Now when I plug in 156, I get 156 take away 12, which is 144. The square root of that is 12. 12 times 2 is 24. Therefore, the derivative on the F curve at 156 is 1 over 24. So here's the beautiful thing. The derivative of the inverse at 12, you're basically just swapping everything. It's going to be the reciprocal. It's just going to be 24. Okay. This question's come up a couple times on ed discussions, and I've made a link to a PDF site because this came up so often in one of the other classes I was teaching that I just made up a discussion for it. And I encourage you to take a look at it. So go to the ed discussions and you should be able to find it. And but it helps explain the geometry, because otherwise, I mean, this one you can kind of get away with working out the analysis, but sometimes you can't. There's one question where it's like some 21st degree polynomial. Well, you're not going to be able to work with that. That's impossible to invert. I mean, you can do it, it's just not feasible. My microphone is kind of going in and out. I don't know what to say. You know what? I don't know what's going on with that. I'm out here in the boonies. Um, hopefully it's okay. I apologize for that. I sound great, but I know I don't know what it sounds like for you guys. Um,
You're sounding okay.
yeah, I'm coming through okay. All right. Again, I apologize for that. Uh, sometimes, sometimes it just goes out. You know how it is. I forget what I was going to say. Oh, I was going to mention. There was like some questions. Let me go back to the question from Edfinity, because there was actually, this also came up in the ed discussions. We wanted to calculate f inverse of x. All right. And we wanted to give the domain and range. Right now, I'm going to come down here. I'm going to copy the function. And I'm going to, right now, state the domain and range. The domain has to be everything greater than or equal to 12. Okay. Because if I plug in 11, I get a negative number. Can't do that. The range is going to be everything greater than or equal to 0. Okay. Now, here's the thing. If I swap, you do the old tradition, you swap the x and the y, and then you solve for the y, you get what looks like the inverse. Okay. And that's true. However, it's not the full parabola. It's only for the right half. Because whatever restrictions are in place for the original function remain true. So here, the domain basically swaps. It becomes x is greater than or equal to 0, and the range becomes everything greater than or equal to 12. So you basically just swap. We're not trying to trick you. That is kind of a detail. Whenever you introduce, like sometimes you introduce a maneuver that actually takes away, like in this case, the radical has restrictions on it, and when you square it away, suddenly those restrictions are gone. Well, not really. Whatever restrictions are in place stay through the entire question. So in this case, you have to kind of keep and remember that this is actually not the full answer. We're only taking the right half. Okay. Let's see. Um, brain is fried. We got about 15 minutes. Any last questions? Again, just chime in or verbally if you have to. I apologize. I'm trying to go through the 26 number 7. Yeah, what was that one? I forget that one. Is that the water one? Um, oh yeah. Okay, let's take a look at this one. This one's I'll show you a way to make this one tolerable. Here's 26 number 7. Let me copy it. It's 2x squared plus y squared quantity squared equals 25 quantity x squared equal to y squared. And we want to find the equation of the tangent line at, in this case, it could be 3, -1. The curve is called a lemniscate, which is actually like a little propeller. Okay, so let's battle this one. So I'm going to show you the shortcut. First of all, you just have to kind of gut through the derivative. So bring the 2 down, you get 4 x squared plus y squared, and then first power, then the chain rule. So you're gonna have 2x. Now, of course, dx is 1. Then you're gonna have 2y, dy dx. Okay, good. Over here, I can actually move the 25 through. Take the derivative, I get 50x. And then here I'm gonna get -50y dy dx. Okay. So far, it's looking pretty nasty. Now, normally you would isolate dy dx, but that's a lot of algebra to hit. What I'm going to suggest you do in this problem is immediately plug in the values. Plug in 3 for x, plug in -1 for y. It's going to make the problem a lot nicer. You're going to get, so 3 squared is 9, -1 squared is 1, so you're going to get 10. Here you're going to get 6, take away 2, and then of course dy dx. Here you're going to get 3, so 150. Now the negative and the negative make plus 50 dy dx. We still have to solve for dy dx, but it's not as nasty looking because I can actually clean this up a little more. That's going to be 40. And then when I multiply it through, that's going to be 240. Take away 80 dy dx. And then here I have 150 plus 50 dy dx. And then I can easily, now it's easy to solve. So I'll bring the dy dx to the right side. I'll take out 150, I get 90. Add 80, I get 130. And I get dy dx is 90 over 130, which is 9 over 13. That's the slope. Okay. I think it wanted the full equation. All right, well, we've got the point. The point was 3, -1. And again, just it's that old linearization formula. I'll just show the insertion steps. And then you just kind of proceed. But the main thing is that in this middle step right here, to go ahead and just put the numbers in now and save your sanity, because otherwise you're going to have to FOIL this out. This is actually going to be an FOIL, and I don't really like that. You know, you can actually save yourself some heartache by just working out the numbers early. All righty. Got, yeah, I foiled it. Yeah, it's a rough one. All right, you know what? Are there any last questions? Um, let's see what we got going here. Would you say the exam is more much? You know, it's going to be an even mix. That's going to be a lot of derivatives and chain rules, implicits, at least one related rate, equation of tangent line, things like that. This one, I think you want to be this is the one test where you want to be really careful on because little errors can mess you up. Somebody asked for 2, 5, number 13 and 14. Sure, I can take a quick look. But let me just say this, that when you're doing your math on this test, just be really, really, really careful with your arithmetic and your algebra because that's where mistakes get made. There was some forgiveness on the first test, but on this test, you really do have to just be really careful. So I'm looking at 12.5, I'm sorry, 2.5, number 12. And I think that was the one that was asked. 13 and 14. Do you have any recommendations for where I can find animations of it? I do not. Google, try to see what they have out there. All right, so this could be our last one. 12.5, I'm sorry, 2.5, number 12, or number 13. Let me copy it. It is y equals sine 9x plus cos 2x. And then 14, and then you want the tangent line at pi over 6, y of pi over 6. All right, so this is a good one to kind of end on. We'll talk a little bit about uh, trigonometry here. So first of all, let's plug them in. So let's plug in pi over 6. I apologize. So y at pi over 6, well, it's going to be sine. So pi over 6 times 9 is going to be 3 pi over 2 plus cos. And then we have pi over 6. So 2 over 6 is pi over 3. 3 pi over 2. All right. Well, that's going to be pi halves is 45 degrees. Pi is 180. 3 pi over 2 is 270. That's going to be on the negative y-axis. So sine of that would be it's going to be -1. Cosine of pi over 3. Again, unit circle, that's going to be 1/2. So the whole thing just works out to be negative 1/2. So the point is pi over 6, negative 1/2. Okay, the slope, yes, you will have a chance to correct your mistakes. The slope, let's do it. So take the derivative. We're going to do derivative of sine of 9x is going to be cos of 9x times 9. I'll put that out in front. Now the derivative of cosine is negative sine of 2x times chain rule, so 2. And then I have to pop in the pi over 6. So it's going to be pi over 6 times 9, which is 3 pi over 2. Take away 2, and then sine of pi over 6 times 2, which is pi over 3. Now, cosine of 3 pi halves is actually 0. So this whole thing drops out. Sine of pi over 3, well, that's one you got to remember. That's 3 root 3 over 2. When I multiply by 2, the 2's cancel, so I just get negative root 3. So that's the slope. So then, again, using the formula for equation of the tangent line, I get y minus negative 1/2 equals rad minus rad 3 x minus pi over 6. Now this one's just going to look ugly because we've got a combination of radicals and pi's. If you want to use your calculator, that's okay. Well, you know, memorizing unit circle, I've been doing this for a long time. It's stuck in my head. I still remember Dodger statistics from the 1970s, but I still can't remember sometimes how to find my way home. All right. So a little pep talk here because I am going to power this down. The test is starting in a couple minutes. Um, you know, I think one of the things about becoming good at math or good at anything is repeated practice. And that's how you get to know this stuff. You just do it over and over and over again until it becomes burned in your memory. And I want you guys, again, on this particular exam, just be careful with the little stuff. It's a lot of little things. That's what you need to be really on top of, okay? You will have a chance to correct your mistakes. Please try to show as many steps as you can in your written work. And now the test actually starts here in about 5 minutes if you want to take it early. It runs through tomorrow at midnight, so you have, what is that, 29 hours to take it. And as usual, I just wish you all the best of luck. In the meantime, please post your questions to Ed discussions, and I'll answer them there. Now, I'm going to prepare those 2 things I told you I'd prepare for those 2 questions that came up. And I'll probably have those in a couple of hours. So thanks again for everybody. I'm going to go ahead and power down. You've all been great. And we'll probably do this again probably next week. The mastery's coming up soon, so we'll probably have one for the mastery as well. All righty. You all take care. Good luck. Cheers. Da, 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 da.